Okay, this is a screencast to go over a few things that I would like you to add to your module or Unit 1, Lesson 1 notes, Chapter 1, Lesson 1, whatever it is. You should have received these back. If you don't have them and you turn them in, they're probably in your box. If you haven't turned them in, then I can't give them back to you. But anyway, I've tried to return everybody's that I got, so make sure that you have those so that you can add a few things. These are mine, so yours probably don't look exactly like mine. But remember, I did ask that you save a little bit of room for some extra notes if we choose to add some later. And that's what we're going to do. Okay, so the first thing is that I made a note that all known elements are found on the periodic table. Basically, if it is not on the periodic table, then it's not an element. Remember, elements are substances that consist of only one type of atom. Carbon consists of all carbon atoms. Hydrogen consists of all hydrogen atoms, etc. And those particular things have certain qualities like its number of protons and things like that. But anyway, if it's an element, you can find it on the periodic table, and it's got a little box with its atomic number and its name and its chemical symbol, that kind of thing. Okay? So, elements are found on the periodic table. There are 92 naturally occurring elements. There are more than 92 boxes on the periodic table because scientists have managed to make some other things in a laboratory setting that do not occur naturally, but there are 92 naturally occurring elements. Okay? I want to talk a little bit about this definition right here, a diatomic element. There are certain elements that like to hang out in pairs when they are by themselves. And those elements are hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. So if you have hydrogen gas, what you actually have are little pairs of hydrogen atoms because they link up and they hang out as a molecule of two hydrogen atoms. Okay? Bromine does the same thing. It makes a molecule of two bromine atoms, okay? They're both colored the same because they're both bromine. They're both colored the same because they're both hydrogen, that kind of thing. Are they actually these colors? No. But these are your 7 elements that occur as diatomic elements, okay? Basically, when they are by themselves, when they're not like bonded to something else in a compound, when they're hanging out by themselves and you just have hydrogen or just have bromine or just oxygen, then they actually hang out in pairs. So oxygen really is written O2 most of the time because, again, oxygen atoms pair up, and so you get molecules of oxygen. Each molecule of oxygen has 2 atoms of oxygen. Each molecule of iodine has 2 atoms of iodine. Each molecule of nitrogen gas has 2 atoms of nitrogen, etc. Okay? All right. With a compound, remember that is a substance containing atoms of 2 or more different elements connected together. And they are connected with chemical bonds. Chemical bonds have to do with gaining, losing, or sharing electrons, but I'm not sure that y'all have discussed that in detail. Just know that they are chemically bonded, and when things get chemically bonded, they take on completely different properties than the properties that they were when they were by themselves. Great example is sodium chloride is Na for sodium, Cl for chlorine. Na, sodium by itself, is a really soft, kind of corrosive metal. And chlorine by itself is a poisonous gas. But if the two are mixed in a compound and form NaCl, that makes table salt, and table salt, obviously, has completely different properties than sodium or chlorine by themselves. So the compounds have completely different properties than the element properties of the individual elements that made them up. Okay, so make sure that you have added that note, and then we're going to go on and add a few things about mixtures. All right. So the first thing I said, and it pointed out in your book that solutions were a type of mixture, and really solutions are mixed so thoroughly that you can consider the individual molecules are mixed together. Now, the individual molecules are not chemically bonded together, so it's still just physically mixed, but they are mixed all the way down to the molecular level, like individual molecules have been blended, okay? Salt water is a great example of a solution. When you make salt water, like you guys did in the lab, you stirred it up, salt dissolves in the water, which means that those crystals of salt broke into individual little molecules of salt that are mixed in with the individual molecules of water, okay? But again, a solution is just physically mixed. It's a mixture. It can be separated. We can separate, and we will separate the salt from the water, okay? Because they're not chemically bonded together. They're just mixed. Okay, we've talked a little bit about alloys, and I'm just going to remind you that an alloy is a special kind of type of solid solution, typically of metals. How do you get a solid solution? Well, you've got to melt things down and mix them together and allow them to re-solidify. And some of your alloys are things like brass, bronze, stainless steel. I think we talked about sterling silver is an alloy. 14 karat gold is an alloy because it's not pure gold. It's mixed with some other things to make it harder. Okay. So that's what I want you to add to your notes. And then I would like to spend a few minutes talking you through a couple of the items in lesson 1 before you proceed to doing the lesson review. Okay, this particular image is on page 6 in your textbook in chapter 1, lesson 1. And it's trying to show you the difference between a solid, a liquid, and a gas. We'll assume that this is an element of some sort because they're just simple little circles, okay? When an element is solid, the atoms are packed closely together. They can maybe vibrate a little bit with a little bit of heat energy that they do have, but they're kind of locked in a certain structure, okay? So they occupy a certain amount of space, so they have a certain volume, and they are not going to like take the shape of their container. Like a lump of carbon is going to stay solid, and it's not going to fill a beaker, for instance, if you put a piece of carbon in a beaker, okay? So solid, you've got your atoms kind of locked together, not a lot of movement because there's not a lot of heat energy to make those little atoms vibrate and move around. Because remember, heat energy is all about how much movement particles have, okay? More heat, the more movement. Okay, if we take a solid and we give it enough heat energy, we can cause it to melt and become a liquid, okay? The atoms are still very closely packed together, but there's a little bit less attraction between individual atoms, and so they're more fluid. They can kind of flow up and down and tumble up and over each other. And so a liquid will fill the container that it's in, or it'll take the shape of the container it's in, okay? If you take a liquid and you heat it up and you give it enough heat energy, then what you can do is you can cause those individual atoms to move further away from each other where there's really no like attraction or minimal attraction between individual atoms, and they're free to fill the container that they're in, and they can take whatever shape because they're going to expand and fill whatever space they're in, okay? So I just wanted you to kind of understand that this is trying to represent the same substance in 3 different phases or states: the solid phase, the liquid phase, the gas phase, okay? Or we can say the solid state, the liquid state, the gas state. Notice that I go from solid to liquid. I still have the little green balls. I haven't changed anything chemically. It's the same set of atoms or the same substance. It just goes from solid to liquid. I've just added heat energy. And from liquid to gas, I just add more heat energy. But this isn't a chemical change, and that's really important for you to understand, okay? Going from gas to liquid, I'm just removing heat energy. Liquid to solid, removing heat energy. But it's still the same substance. So these are all physical changes, Okay, I also wanted to talk to you about this diagram because it says, what's the difference between diagram A and diagram B? Remember, they typically just use little balls or spheres to represent individual atoms. And so this would be a pure substance. It's just one particular type of element because all of the atoms are the same. And it could be anything, I don't know. But interestingly enough, this is also an element, okay? Because they're bonded, but it's two of the same, two of the same, two of the same. This is going to be one of our diatomic elements. That's not y'all spell, that's just in the background. Okay, so this is an element. This is also an element, but this is one of this, I don't know which one, but this is one of the diatomic elements because whatever atom this is, it likes to hang out in pairs. So it's either hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, or fluorine. Because remember, those are the ones that we talked about that like to hang out in pairs. Okay? But same color, so same atom, they're just bonded together. So they're hanging out in pairs. This is also an element, but they're not hanging out in pairs. So this is just how they would draw a regular element, how you would draw a diatomic element. Okay, once again, this is on page 9. It's another image. And I'm hoping that you guys can see that 2 and 3 represent individual atoms of some element, okay? Number 1 represents some sort of compound, a single molecule of a compound. Maybe this is water. Water is a single oxygen and 2 hydrogens, okay? But it's obviously an atom of one variety bonded to 2 atoms of some other variety. So this is a compound, okay? Over here, this is a ball and stick model, again, of a compound. I've got an atom of one variety, this dark blue one, bonded to 4 of these other types of atoms. They gave an example somewhere maybe that this might be methane, which is CH4. But again, it's, in this case, if it is methane, this would be 1 atom of carbon bonded to 4 atoms of hydrogen. Okay? So here's the way we're going to represent an atom of an individual element. Here's the way we would represent 1 molecule of some sort of compound. Okay? All right, now I want to go down to the bottom of page 9 and talk about this for just a second. First of all, remember these 2 guys are both elements, but I'd like to point out that they have made a little mistake here because they haven't accounted for the fact that oxygen is one of your diatomic elements. So if we really want to take issue with this, these should be hanging out in pairs, just like our nitrogen atoms are hanging out in pairs, okay? So I'm going to stop real quick and I'm going to fix that. Okay, so I made it more accurate. It should technically be O2 because remember, oxygen is one of our diatomic elements that when it's all by itself as oxygen, it'll hang out in pairs. If I take nitrogen and oxygen, which are the 2 main components in our atmosphere, and mix them together, they'll look like this. Okay? This is a mixture of 2 different elements. Okay, over here we have carbon dioxide represented like this because it's 1 carbon and 2 oxygens. And then we have water represented like this, 1 oxygen and 2 hydrogens. And we could mix these guys with our other mixture here, and now we have a mixture of both elements and compounds. We've got 4 individual types of things here. We have nitrogen. Oh, and I got to fix my oxygens. We have nitrogen, we have oxygen, nitrogen gas, oxygen gas, carbon dioxide, and water. Okay? So this one is just a mixture of 2 elements. This is a mixture of both elements and compounds, if that makes sense.